the Enterprise Digital Podcast with Ian and Barclay Ray, navigating the ever-expanding service management maze.
Hello, here we are. Welcome once more to the Enterprise Digital Podcast. Boy, do we have an interesting show for you today. I am still it's episode something. I don't know which, but it's a high number. It's a big number. I'm Barclay Ray once more, and as ever, I'm joined by the intellectual Ian Aitchison.
Intellectual. Thank you.
No.
I'm not sure how to take that.
I was looking for another word that ended in actual, but I've come up with intellectual. That's enough. Ian, what's happening in your world? How are you doing?
I'm doing very well, thank you. Yes, although struggling with technology today. We're trying out new platforms on our recording of podcasts, and it's not easy, is it? It's not easy with these technologies.
Yeah, I didn't hear myself there, which is fine, but that's
it'll be there in the edit, so don't worry. That's the great thing. So
we always talk about on this podcast, we're always talking about stuff to do with technology and service management, delivery, and people and AI and all sorts of stuff. And we may or may not do that. But before we do that, we always have a bit of a sort of interesting diversion. And Ian, that's normally your thing. And I'm hoping that you've got something this week.
I do, but I think we're also going to turn the whole format of this show upside down, because usually we can start with a little interesting snippet about things that have been discovered or invented or innovation around the overlap between technology and science and biology and innovation. And then we go to talk a lot about IT and service and automation and AI and management and these areas. That's usually the main topic. So I do have a little bit of that first thing. I was going to talk about how bees know, and it's been proven from research that bees can identify changes in time, and that you can guide a bee through a maze by flashing different periods of light, and they'll follow the long light once they're trained. And it's a fascinating story, that. But actually, we're not going to spend time on that because, as I said, this week we're going to turn it all upside down, aren't we? Because this week we are focusing on, as I said, the overlap between science, innovation, biology, technology.
Okay. Well, let's go on with it. Let's bring in our guest this week. We're delighted to welcome Dr. Ewelina Kurtys. Hi, Ewelina. How are you doing?
I'm good. Thank you so much. Hope you do.
An advisor for an organization called FinalSpark.
Yes.
And we're going to talk about some quite interesting stuff that's really out there. But before we do that, let's get introduced. Can you tell us a little bit about yourself, your background, and how you got to be doing what you're doing now? That would be really helpful to start the conversation.
Sure. So I'm Ewelina Kurtys. I come from Poland. I started my studies there, but after I left, I did my PhD in Netherlands. And after I came to England, to London, to do postdoc, a project at King's College. And later I decided to leave academia because I was always curious what is outside. So I have background in neuroscience, but I was always curious about the external world to research. And London, I think, is a perfect place for this. Because there are many opportunities. Actually, anything you want, I think you can find there. And I discovered the world of startups. I had no idea actually before about this, but I realized that you can work in a small company or set up your own and have a lot of flexibility. You can create your own life, which I enjoy a lot. And after working in some small company in London, I decided to leave and set up my own company, because I think it's a very friendly environment in UK for doing this kind of things, which I highly appreciate. Because in Poland we have a lot of bureaucracy, so we always enjoy the fact that we don't have it here. I also discovered artificial intelligence because there were a lot of startups and interesting events in London. I saw people do very cool stuff. I also met the founders of FinalSpark at one of the events in London, which was AI Summit. That was before the ChatGPT, so it was really interesting to see what people are doing. I think now it's a bit boring because One AI problem is LLMs, large language models, so it's not so exciting anymore. But before it was really exciting and really eye-opener, what you can do. So I started to study AI. I started to work on application of what you can do in industry. And then later I started to work on the future of AI with FinalSpark. This is how we imagine AI in 10 years, to build computers from living neurons. So this is combination of neuroscience and engineering to create some totally new device, a totally new type of computer, which will be 1 million times more energy efficient. So the AI will be more accessible because there is a problem which maybe we don't feel yet too hard, but AI is actually very expensive. And today a lot of models which we are using are actually underpriced, you could say. They are much cheaper than they should be. And for example, OpenAI is losing a lot of money. They lost around 19 billions time because of course we have to they have to give them almost for free at the beginning to ensure adoption. However, AI is much more expensive than we think. And we can expect in the future the prices become real. To make sure that AI is accessible for everyone, I think this is the really most important problem. Some people mention also environment, which is also important, but I think the most important problem we solve is accessibility, that everyone can use AI. Because when it becomes very expensive, it will not be for everyone. And that I see as the biggest problem. So we want to solve it. And actually, there are many people who try to solve it. We are not the only one. There are many ideas actually, and there is constant effort also in software industry and in digital hardware, how to optimize things, how to use less energy for generative AI or other types of AI. And we think that our solution is extreme. So let's say for the next 10 years, we can see some little steps forward for sure. Improvement of software, maybe some new digital chips, maybe even analog hardware. But what we will provide will be extreme because it will be 1 million times more energy efficient. So that will hopefully solve the problem of accessibility of AI.
That's a very noble endeavor. You talk about accessibility, but also sustainability, effectively,
Yes.
using less energy because there's so much power being used for this. But you're now based in Cambridge, is that right?
Yeah.
Yeah.
Actually, Cambridgeshire. Oh, that would be more precise. Yes.
Yeah. Okay. Well, thank you for that introduction. We'll get into the conversation, and as you say, you said it was extreme. It is quite out there against your solution. So let's do that. You're already having a nice cup of peppermint tea, and we'll have a wafer biscuit and some lime cordial, and then we'll carry on. We're introduced. We've heard a little bit about your background and some of the things that you're doing and interested in. I'm always the one that asks the sort of old person's question of how does this work? I looked at your stuff and my goodness, it's definitely different because it is actually looking at a biological approach to technology, not just digital, certainly not analog, but not just electronic. We're talking about using neurons, using different types of biological sources to do the computing. And as you say, if it's going to be 1 million times or a very high number of times more efficient and effective, sustainable and accessible, that's all fantastic. But can you just give us a quick, imagine I'm a complete idiot. I know it's difficult to imagine, but if I'm a complete idiot, can you explain what you're doing with the neurons and how that, and the biological approach to computing that you guys are working on? That would be helpful to get started in the conversation.
Yes, so we culture living neurons the same as we have in our brains. They are just living cells. This is quite normal in biomedical research. People are using any type of cells from the human body, and you can do a lot of experiments with them. Our tools are not new for biology, but the purpose is new, that we want to build computers. So not many people are thinking about this yet. And we put neurons on electrodes, which is also not new because that's electrophysiology. It's something what people were doing since 100 years to see how a living tissue reacts on electrodes, how we can process signals. But again, the purpose is different. We put neurons on electrodes because we want to try to program them like computers. We want to send them electrical signals and we want to receive response. And we hope we can use it as a computer processor. So the future biocomputer will have processor built from living neurons, not from silicon logic gates as we have today. So that's in the nutshell what we try to do.
Let me jump in and play that back, because this is just fantastic, extraordinary stuff that you're doing. You said in the introduction that you're on a mission to make AI accessible and cheaper. I love your comment that you said AI at the moment is a bit boring. And we talk about AI so much. That's the LLM, the large language model thing, can be seen as a bit boring. Well, you're not just talking boring things here. What you're saying is your solution to how you will make AI cheaper and more accessible is by building compute devices based on living neurons taken from or built from natural animal cells or human cells that provide the logic decision. So not silicon AI, but biological AI. Am I getting that right?
Yes, absolutely, it's correct.
Wow.
Are these based on cells extracted from people? How do you create those cells?
So we buy stem cells, and stem cells are derived from human skin. And this is the process which is actually already commercialized, and it's widely used by labs worldwide, but of course for biomedical research. You can buy such stem cells and produce any cells you want, including neurons. So we do something called differentiation. That's such a technical term. So we make from stem cells, we make neurons. And yeah, that's how it works.
And then you wire them up.
But it works, yes.
Yeah, you wire them up, and then you can feed electrical pulses in, and you can receive responses back. So I'm picturing in my mind like a data center,
Yes.
but data center. And I'm sorry, this is a terrible way to describe it, but a data center full of natural medium culture dishes or whatever wired up. Is that what we'd see if we went to your offices?
Not yet. But it's exactly how we imagine the future. We want to build a huge biocomputer which will be central. And maybe we can build actually many of them. Once it works, we can scale it if need. And so it will be huge structures from living neurons, much bigger than a human brain. And it's not going to be brain because some people say, oh, you culture brains. That's not what we do. We just use the building blocks of a brain, which are living neurons. And we imagine it will be huge and accessible remotely, the same way as today cloud computing. And of course, there will be a lot of liquids and a lot of stuff to keep cells alive, because every living cell, they have to be in the liquid environment. They need to have nutrient, oxygen, everything. Today, we have them very small. So actually, we have a little blob of cells, 3D structures, 10,000 neurons around, a 0.5 millimeter diameter, very small. And we put them on electrodes, only 8. So it's very small setup. But for current research, we believe it's enough.
Wow, it's extraordinary stuff. And this is already, having done some research on this is already available to research organizations that sign up with FinalSpark, and they can access websites that are using this compute power today. Is that right?
Well, our lab is available remotely for fundamental research in how neurons process information signal. You cannot really process information, so you cannot run software on that. It's rather for fundamental research. So you send electrical signals to neurons, also chemical actually, because you can send them also dopamine, for example, or serotonin, and you can measure the response. You can try to interact with neurons. So that's very fundamental research. And yes, we are very proud. We invited universities from 34 projects. We selected 9 universities, and actually one of the UK university in Bristol already published a paper. There is a blog on our website, finalspark.com, if you want to check the details. So we are very happy for this. That was the motivation why we invited researchers, because we wanted them to publish, to do something and publish, and the work based on our lab. What is even more interesting, we have also clients who pay us to get access to our lab. So there are also some companies where R&D teams are interested to explore what is on the edge of technology. And they also doing projects and they pay us to get access to the lab.
On Ian's idea of it just being a giant brain data center, does the computing power or logic part of it, is it going to work the same way as existing processors, or do we know yet? Or is it going to have some other kind of aspect of it, is it just going to be super computing done biologically, or is it actually going to have a different way of thinking or processing data?
Yes, for sure, encoding is different because we know that neurons encoding information in time and space in form of spikes. So they have these spikes, which is basically changes in voltage on the membrane of the neuron. It matters when in the brain and at which point in time and space they are active. So for sure, this is totally different. So the processing of information is different. That's why it's so efficient. Also, that's why it's so difficult, because we have to figure out totally a new way to deal with programming. So it's both advantage but also disadvantage of neurons.
It's a little bit like quantum computing in that way, because you're moving away from a binary model to a sort of infinite number of dimensions. So you don't just get ones and zeros.
Absolutely. That's exactly the same idea, the same problem, long-term project. That's why it takes so many years. Quantum is just a bit more advanced, let's say, because it's maybe 15 years older as a field, but it's exactly the same idea. You have totally different hardware, so encoding is totally different. So you have to figure out a different way how to do coding, how to program these machines. But they are also superior. So yes, quantum is kind of similar. But quantum, I believe, will be for different applications, because quantum is very fast and neurons are not fast. So they wouldn't be suitable, for example, for cryptography, which is believed to be a great application for quantum. But neurons are quite slow, but they are very efficient when it comes to complex analysis. So this is where we see the advantage of living computers. That's why we believe in generative AI, because generative AI, let's say, doesn't have to be always fast, but you appreciate if it can analyze complex problems. And if you can save energy on that, that I believe will be helpful.
That also extend to how we learn, because I mean, I know that this aspect of our brain in terms of how we retain some connections better, you know, the way that we engage with, you know, that you remember things better if you've experienced them than if you just read them, for example. Is there some way that you'd be able to mirror that, or is it trying to just be faster and more efficient?
So our dream is to match the performance of digital computers in some tasks. These are going to be fast but energy efficient. So we actually would imagine, our dream is that end user doesn't feel the difference. And I generally believe that the future will be that way, that we will have a lot of different hardware. Because you see this not only in biocomputing, you see also other fields. People are doing customized hardware, customized chips, also digital, or even some people play with analog hardware.
Yeah.
So I believe the future will be a lot of variety of hardware, also quantum computing and biological computing, but hopefully for the end user, at least this one who is interacting with the software, it should not be a difference, but maybe it will be cheaper. So that's what is important, actually.
So you're not building brains here.
No.
What you're building are alternative processing mechanisms.
Yes, absolutely.
Yeah, fantastic. Now, one thing that naturally comes from this is people can be quite squeamish about this sort of topic. You talked about stem cells and growing and wiring up wetware. And actually, for the first time, wetware becomes real. It used to be a joke back in the 90s. You know, is it hardware or software? No, it's wetware. You joke. It's the human being that was the cause of the problem. You're actually introducing real wetware. But for example, I'm a big advocate of the future of lab-grown meat and the potential it will have for the environment and just a worldwide food productions, and could be amazing, but everybody's quite squeamish about that topic. Do you get much of that sort of feedback when you talk about this? Do people go, it's human brains. Is there much of that you have to tread carefully around?
It's funny, I don't know the word squeamish. It's funny to learn, but I know what you mean. It's cool.
Yeah.
So yes, absolutely, we get this kind of comments, a squeamish impression. Because yes, indeed, there are two reasons, I think. One reason is when there is biological tissue, especially human tissue, there is always people who find the controversy in this. And another reason is that people, I think, are generally reluctant, afraid of things which they don't understand.
Yeah.
So there is actually this phenomena is observed in technology all the time, that everything what is new is actually at the beginning creating resistance. Even iPhones, even whatever, internet, emails, things which today we cannot imagine life without them. At the beginning, they were controversial, actually everything, even the medicines, modern medicine, anything. You can imagine what was the progress of human technology. So this is absolutely normal thing, and we are not surprised with that. And this is why actually that's one of the reasons. One reason is fundraising, but the second reason is actually this, that we doing all these podcasts, and also we talk to journalists, and we try to be transparent as much as possible so that people can see really what we do, and they hopefully will not be afraid of this. For example, on our website, you can see on FinalSpark.com, there is a section live, and you can see the live view from our lab. You can see exactly how it looks, what we have. And we believe that this kind of transparency and explanation, explaining to people is actually helping that. But yes, we get a lot of comments.
And I saw a YouTube video, I think there might be a site somewhere, where people can see the results of this with a butterfly.
Yes, absolutely.
Which an animation of a butterfly flying and reacting to, I think if you move the mouse, it reacts and flies in different directions, and the reaction and the decision to fly from your, what are they called, organoids? Is that what you call them?
Yes, we call them organoids.
So people can go to your website, and if they look on YouTube, they can actually see this in action.
Yes, absolutely. It's a web application. It doesn't work always because it's connected to real neurons. Sometimes we don't have capacity in the lab, but if you can enter the application, that means it works. Then you can interact with the butterfly. You can decide the direction where it will fly. And then the signal is sent to neurons. And depending on the signal of the response of the neurons, the butterfly will fly or not.
Amazing. What's the timeline for this, looking into the future? Obviously, you're at groundbreaking startup innovation, but you're very connected with universities and research organizations. You're getting great investment. What sort of timeline into the future for this starting to be, I wouldn't say necessarily available, but more received by a wider part of the population, more widely adopted, having an impact into more people's lives, do you think?
So we believe in 10 years, the computer will be ready. So yes, it will take some time. Before that, I think engineers will be affected, maybe, who will work on that. But before that, the end user, I think it will take around 10 years.
Do you think there's any, when you're talking about the computer and you said it's going to be a big computer somewhere, I mean, is there any further development you think where, we could, given that it would actually be a biological solution, are there options for that to, I don't know, augment people? Maybe built into a hat or something, you put it on your head and you've got an additional level of intelligence or capability. Is it just going into the computer market, or do you think there are further options beyond that?
Well, personally, it's not our objective, but yes, it's possible, because when we learn how to program, we basically want to program living neurons. So we want that they learn some task in vitro in the dish. But if we learn this, it's actually, this problem requires us to understand the language of neurons, which still is unknown. And that's why it's so difficult. That's the biggest challenge. How to teach neurons. And how to teach neurons is to understand how they encode information. This nobody really knows what the spikes mean. We know a lot how they are processed, but not what does it mean. So when we solve this problem, maybe one day we had this kind of ideas that someone will be able to upload some information into our brains, maybe in new language. Who knows? That would be amazing. I really believe it will be possible one day, but for sure in very far future. And it's not our objective, but for sure our work can contribute to this progress.
So just onto the kind of business side of it for a moment, if it's going to take 10 years to get this to market as a product, as something that's, financially viable, commercially viable, how are you going to live and eat until then? What is it basically getting, investment in advance, support from financial institutions and universities and so on, or are you going to be able to sell much between now and that period? Even you might bring it into 7 years or 8 years or even 5, but from a commercial perspective, that's still quite a long period. What's the plan in terms of moving that forward?
How are you funded?
Currently, we are funded by the founders, Fred Jordan and Martin Kutter. They started FinalSpark, and they fund this with the money which they get from another company, AlpVision, which is very successful in digital. So it was working immediately. The technology, it didn't take so much time as FinalSpark. So they fund the project. Of course, because of this, we are a very small team, only 6 people, and everything goes slowly. And with this, it will be difficult to build a computer in 10 years, but who knows, maybe with LLMs we can speed up. But actually we search for investors. We search currently for 50 million Swiss francs to accelerate our research. And this money is needed to hire more people, to have people to work on this problem.
It is the classic startup model. It just happens that the technology you're innovating on is wetware and soft technology rather than building a new social media platform or whatever that may be. Your startup
Yes.
is focused in that area, but it's the same thing. You look for funding, you go through funding rounds, investors, as you move to market, and eventually you turn income and eventually a profit too. Yeah, amazing stuff.
It's a long cycle though, isn't it? 10 years is quite a long period to wait. If that's when the product will be available, the return on investment would still be beyond that. Do you think you can speed it up if you have more people or if you have more?
Yes, maybe yes. It's hard to say because 10 years is really long. So it's always an estimation. But for sure, with an investment, we can speed up a lot. Because people is the biggest factor in such projects.
And let's remember where you started this conversation today. The reason you're doing this particularly is the current AI capabilities, which are remarkable and incredible with large language models and generative AI, is incredibly expensive.
Yes.
It's massively power draining, and power is a global problem anyway, really, how we generate power. So what you're saying is that this solution could enable us to continue to move forward with things like the AI trajectory that we're on, but without that massive expense and overhead that means it can only be run by the 5 or 10 mega vendors in the world and all of the political issues around that. It becomes available to much smaller organizations. They can build their own much more cheaply.
Yes.
Any kind of ability. That's incredible. I was also just thinking to myself, just chuckling slightly. I used to work in an organization which introduced a IT automation platform called Neurons. It's all software automation, detection and remediation. We are talking about almost the same use case of computing, but genuine, real, absolutely real neurons, which is, I'd still just find startling. But it sounds like, I mean, Barclay, you say 10 years is a long time. I think on this sort of journey, 10 years is a really short period of time. I mean, we could still be doing this podcast, and the processing behind this podcast could be from Ewelina's work in 10 years' time.
Yeah, I mean, I the question is just, the pace of change these days is so fast, and you can see these things accelerating, with new developments. One question that occurred to me as well is, what else is happening in this space? I mean, what other kinds of, innovation would you see maybe in a competitive point of view? I mean, you're talking about a biological approach using neurons. Are there other areas where you think that perhaps people either are working or could be working to develop computing power using other types of capability or tools?
Yes, absolutely. So we have, to our knowledge, 2 competitors, Conico in US and Cortical Labs in Australia. So they also, especially Cortical Labs, they also wanted to build computer from living neurons. They are still building and very actively. And when it comes to brain-inspired computing, we have a field of neuromorphic computing, which is active since maybe 15 years, maybe even longer. And that's a field where people try to do software or hardware, which is inspired by a human brain, even more, to optimize. And there are some technologies which are working. People try to use this spike approach to encode information, but still nobody really knows what spikes mean. So usually you have to hard code the spikes. So you say this spikes mean this, another spikes mean something else. So you hard code this. But yes, there are a lot of trials, and there are also some successful proof of concept. And I think some neuromorphic chips are on the market already. So yes, this is the direction. Of course, they are not so extremely efficient as real neurons, but this is the direction in which we are going. And all this helps us to understand better how neurons process information also. So this also can contribute to the final effect of biocomputing.
Amazing. And from your description there, back to your core business, you have two competitors around the world, which means it's a competitive market, which means they'll be fighting for investment to move faster, to be the first to introduce to the market, which is what accelerates innovation.
Yes.
Having competitors is a good thing. It's, it drives.
Oh, yes, we are very happy to have competitors.
Yeah.
Because, also in such a new field, it's really important actually not to be only one, otherwise maybe we would be crazy.
Yeah. So for our core audience, Barclay, and our core audience who are probably centric around IT and working practices and service management across the enterprise and those sorts of areas, they're often worrying about providing a good digital experience to employees in an organization.
Yes.
The issues they may encounter with technology are not going to go away, but the back end behind that technology might in the future be provided by neurons. The front end won't change.
Yeah.
Front end will change, but the back end might pivot to a much cheaper model.
Yes.
Well, that was going to be the one other question. I thought I came up with a good question, which is that what we deal with is people that run systems very much. They look after, they support, they manage, and they tend to be naturally have come from working in technology. And are we saying that to support and run these systems, we will now need biologists, we'll now need a completely different skill set to be able to maintain and support these platforms?
Yes.
Do you think it will be a new subset or a new discipline in the sense of like understanding the biology side and the computing side?
I think today is important at the R&D stage to understand. But I believe once we have biocomputer, these people will be niche. And I hope there will be, now for sure, like in the digital, in the past you had to understand really logic gates to code, but later we developed some high-level language. So I believe there will be high-level layer in the future, and it will be much easier.
But it may not be a core skill of people working in a IT service desk, in a financial services company. They'll continue to deliver a good digital experience to their employees and customers and so on. The difference will be the back-end technology.
Yes, but you don't have to, the same like today you code on your computer laptop. You don't have to know Verilog or some other really low level programming. You can program in Python, which is very high level. And I believe the same will be in biocomputing. Maybe even Python will be enough. Then the system will compile everything to the hardware automatically, like it's done today in digital.
Do you think, just finally on this, because I'm starting to think about it, it's kind of blowing my mind. In terms of the long-term viability of those neurons, how long would they last? Would they have to be replaced or updated or maintained in some way? Or you said they have to be fed and watered effectively, but is there going to be a life cycle for them that would then need to be replaced?
Yes, this is a very good question. Actually, we know from nature that neurons can live up to 100 years. So, because in our brain, we have the same neurons through our lifetime. So we know they can live much longer than now. Now we can keep them in the lab alive for 3 months. We had some extreme examples of 7 months, but these are outliers. So we definitely want to extend this time, but we also think that the biggest challenge is programming neurons. And once we can do this, then we also believe we will be able to exchange the parts of this hardware if it's dead. Yes.
So we're swapping out one neuron for another.
Yes.
It gets to the end of its cycle. Wow. That's fascinating, completely fascinating, mind blowing stuff. I might need to go and lie down in a dark room now and just contemplate all that. Thank you, Ewelina. That's
Thank
just
you.
given something to think about. Where you mentioned FinalSpark. I mean, are you on LinkedIn or some other way that people can contact you? How make contact with?
Yes, definitely. I'm on LinkedIn. Also, our website, I think, is a good source of contact. So if anyone is interested, we are always happy to get in touch.
Well, I'm sure we'll add that to our notes of the podcast. Okay. Wow, fascinating stuff, Ian. And I can see it in your face that this is brilliant.
I do. I think this is fantastic stuff. I think it's both interesting and exciting, and I will certainly be following FinalSpark much more closely. I thought this would be a 50-year timescale. So 10 years. I was just amazed how far advanced this technology is. So, yeah, very interesting. Great to have you on board. Now, we typically wrap up, don't we, Barclay, with a trivia question. And we have warned Ewelina about this, but we often spring
Ask any question you want.
we spring a completely random question at the end as a thank you. And I'm just trying to think of one that would be appropriate. And I'm not sure I can find something connected to this topic.
Well, maybe not connected, but I mean, you live in the UK now, and you're from Poland originally. What surprised you most about the UK to live here?
I don't know if it's surprise because I lived in a few countries in my life. So I'm kind of always prepared that it's different than at home. But I have to say what is different about UK, what I really appreciate, what I learned actually when I come to UK, because I'm a very direct person. I like to speak what I think. And I think when I was younger, I was sometimes too harsh in expressing my honest opinions. And what I learned actually in UK to be kinder than before, because I realized that actually it's not a bad thing. Some people are complaining that, small talks, that is a waste of time. But actually, I disagree with this. I think it's really good. And I saw it when I was working in London. I saw how much it can improve the environment when you have actually people are nice and you don't need to always know what they really think. And it's good. It's really good. So I really appreciate that. And also, as I mentioned before, that you have much less, at least from my point of view, you have much less bureaucracy, which when you have your own company is really amazing, especially when it's very small. So I think this is fantastic. And that was maybe surprise because I'm used to, that in Poland we always have huge piles of documents. And I know that now there is very strong digitalization in Poland. So actually things are changing. However, it's still a lot of bureaucracy compared to UK. So this was actually a surprise, but it's very, very good surprise for me.
Surprise to me. Run businesses in the UK for about 30 years, and it's isolated. It's probably not too bad. Silly.
No, trust me, it can be much worse. When I talk to people who have companies like in Poland, you can have such amount of bureaucracy you can't imagine. Yes. So I think it's good to appreciate this. I think it's nice. And you have long history actually of, let's say, entrepreneurship. So I really like it.
That British delicacy in being very subtle about when we say things, we're not so abrupt. That can be good as you describe it. It can also drive a lot of people nuts. I mean, I've worked with many people around the world. You're so British, just say it. Just say it like it is. Stop dancing around.
Actually,
tell me.
Because sometimes I really don't care what actually people think. And when you don't say things negative, the atmosphere is nicer, at least in my opinion. So yeah. I think I like it.
It's a way of
building, isn't it? It's establishing rapport and all that kind of stuff.
Yes.
All right. Ewelina, it's been a real pleasure to have you on. Thank you for your time. We look forward to keep an eye and see what's happening and how long it will be before you can get that stuff to market. But for now, thank you very much for joining us.
Thank you too. It was a pleasure.
Thanks. Bye-bye.
And we'll see you soon on the Enterprise Digital Podcast.